I will share presentation right now, or at least try it. Okay, I am not go here and here, and I am going to try to the slideshow. And no, it's probably not going. I will share one more time. I was hoping that doing that sharing I will be able to manipulate, but no. I will have to change sharing during the lecture. Okay. So today I would like to talk to how to obtain translation diffusion coefficient from NMR relaxation data practical guideline. And well, first, I would like to and I cannot change the. Okay, short reminder on theory, then example do of fitting of the 3D diffusion, the translation diffusion, and then to do example fitting of 2D diffusion. Why do also 2D diffusion, so-called surface diffusion? Because very often we are thinking whether we have 3D diffusion or 2D diffusion, or usually it's sometimes, well, the data are not clear whether we have one or a second model. So it is sometimes beneficial to have the possibility to fit another model. And as Professor Crook told you before, that there is never a very rare situation that, well, both models fit perfectly. But sometimes the situation is that both model fit incorrectly, or to be more, not exactly ideally. And then you have to decide which model is better. Therefore, well, it's quite good to be able to fit both of the models. Going further, a short reminder on the theory. What is diffusion? Well, diffusion is net movement of anything, for example, atom, ions, molecules, energy, generally from region of higher concentration to region of lower concentration. Obviously, it is a reminder of the basics, and well, diffusion is driven by gradients of Gibbs energy. In other words, we are moving. If we usually start from one area, we then have to we slowly. Here we have area with the bigger concentration, and by the Brownian motion or other motions, we slowly diffuse to other area. So in the end, entire region have similar concentrations. Of course, it takes some time, and the bigger difference between concentration in this area and this area here, the faster will be diffusion, faster will be change of diffusion. As we can see, on the beginning, the change of is quite fast, then it slows. And this is described by so-called thick first law of diffusion, which, well, when we are we describe so-called diffusion flux, so amount of substance which flow through area per second. So how much of the substance is going through some area. Then we have gradient of concentration. So how it change concentration through space, because the gradient is wrote describing the parameters of space, not time, but in space. And we have here in other words, diffusion coefficients. These parameters which translate how fast this particle moves, how this, well, to be more exact, how fast this particle diffuse, but in this case, we are interested more in how fast it moves. And of course, the unit of diffusion coefficient is metr square over the second. Important is now to what we should expect, what values we should expect, and in the normal temperature. So let's call it around the 25 Celsius or 298 kelvins. We should expect something like that for the liquids. And very important is that, well, quite important is to know the diffusion coefficients for water. Why it is important for the water? Because if our results shows that some actually average here should be m square. I just realized I made mistake doing presentation, but if our result is around bigger than water, then maybe we have some mistake. Water diffuse very quite fastly, and very often it's not easy to get the diffusion coefficient bigger than water. Okay, and a reminder of the basic, which we was talk during one of the previous of the previous lectures. We sometimes can describe relaxation rate as such function where CDD is dipolar relaxation constant and H from the oh, I forgot the word, of course, is spectral density functions. And spectral density function is Fourier transform from the correlation functions. And you very often this spectral density have two parts. One intramolecular and second intermolecular. Very often for the intramolecular, we are going to the so-called rotational diffusion, which can be how to say, usually simplified to that equation, which was to BBP, which was shown very few times during this lecture in previous. I am showing here, it's because why we are showing rotation, because when we are doing the when we check this against relaxation rays, usually we are having not only translation diffusion in our sets, but some other type of motions. Very often in these data sets, we have this addition, the rotations. Rotations, and therefore we have to include in our model such spectral density from the spectral density from, well, let's say rotation. The model for three-dimensional translation diffusion is like it is like that. We have here integral, and the translation diffusion coefficients is put here in this tau translation, because tau translations is calculated like that, like that, where we put distance of closest approach, so how close two particles will be close to each others when they will be interacting, when they will be exchanging energy, and this diffusion coefficients here. Both of them give us translations type, and in our these parts here. These parts here all is well, they are constant physical constants. When we check, well, we can always check them in the physical tables, or I don't know, even in there, of course, even in the Wikipedias. So they don't change. depending on our, if we, of course, it will, the geometric factor will change depending whether we, what resonance frequency we change, we check whether it is one hydrogen or other atoms. But when we are checking just hydrogen resonance, it will not. This is a physical constant which will not change depending on the systems. This is the last part which change depending on our system. It is the number of hydrogen 1 nuclei per unit of volume. So how much, how many of the atoms of hydrogen is actually not atoms, because nuclei. So how many nuclei is in per unit volume. And of course, if we here we have how these results looks on the this spectral density function looks on the plot, where on the x-axis we have frequency, and on the y-axis we have normalized spectral density. As we can see, it slowly goes down. Then around the invert tau trans, in slow it starts descending faster. Okay, so going further, when we see, of course, it is when we see that this is some shape, but well, there is some curve. When we are seeing this in our results, we cannot always, we don't have some calculator in our eyes, which we say, okay, I see this such curve, and this means that this will be in translation diffusion, because usually we have to fit the model. But the problem is that, well, we have here to this integral, so the fitting is a little more problematic. Usually it's not so easy to fit these results. So how to check firstly whether we have 3D diffusion in our data. Then it was talked during the previous lecture that if during the small frequency, here is the limit, theoretical limit, whether in theoretical limit, we expect that the spectral density would be more or less the proportional to element or element of rotational speed, rotational velocity. So we expect, and if we change the x-axis to the to um, to to this element of the from the rotational speed, we should expect that it will it should be proportional, and as we can see here, it is proportional. Of course, as we said, it depends only in this small. This is the first well, limit. It's for the smaller. It is proportional for the small frequency. Secondary, well, as we said before, usually it is not like we have only one type of motion in our sample. We have very often samples which will be different to each other. If they are different, I'm sorry. If, for example, we have translation and rotations, and if we so it can this will be as we this can be disturbed, but if, so it's not always that it will be such very easy curve or looking very good on linearity, but it is the first sign to check it whether it is so-called fingertips, which will show us whether or not to check for the 3D diffusion model. And here, for the small rotational velocity, for the small frequency, we can change, we can approximate result of relaxation rate from such spectral density with such results. When we here, so, well, as we can, this is physical constants. This we can try to calculate. This is a model for 2D dimension, 2D translation diffusion. So in other words, translation diffusion on the surface of the macromolecules. And well, if we look on it, this here is this spectral density described on the logarithmic scale. This, while it is a logarithmic, and we know that for the if this this limit is well is correct, we can expect that the spectral density is more or less proportional for the logarithm of the rotational speed, angular speed. So this, and one more time, as in this case we look for such representation data to check whether we have 3D diffusion model. So in case of the 2D 2D translation diffusion, in other words, on the surface, we usually will check whether in the case of logarithmic scale we can see proportional. And since we usually see it on the logarithmic scale, it is well, we are doing this automatically. Of course, if the life would be very, very good if well, we just have to check whether it's proportional in the case of the uh, the square or in the case of the logarithm. But as I here have generated some data on the case of the using the spectral density. And to be clear, they are just artificial and generated. So here we have a case of the just just 2D translation. The red ones are just 2D translation diffusion with rotation, and blue one are just 3D translation diffusion with rotations. Why I did this? To show you that if I will try to fit the model to the wrong data, because they are generated, we are assuming we know how they were generated. But despite that, I was able to fit this result very, 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 very good. Of course, it's not perfect when we are, it's not perfect, but well, it's look for the first glance when we are, we are putting, we have results. So our first thing which we are doing, we are trying to fit two models, and we can see, oh, they are fitting, and then we actually fitted wrong model. And frankly, if we would look for the fitting 3D translation with rotation to both of the set of data, well, while it is not exactly as good as previous, we can also fit it. We can also fit it very, very good. Well, what is interesting here is actually that these fingerprints, well, they are actually behaving little better than, well, full sets, because the area of proportionality is much larger for the correct model, and the wrong model, in this case it is right model, is actually we expect here linearity for that 3D translation diffusion. And as we can see, this diffusion, I don't know, do you see my cursor or not? If could someone
Yes,
write?
we do.
Yes. Okay. Is this rotation and the linearity here is much further in area. The same here we can see in the case of the fitting to logarithm from the frequency to 2D, which we expect to show these fingerprints, is much longer. So therefore, usually when we are trying to fit data, it's always to remember, it's always very often we don't have to just fit data. Oh, model fit, so is everything is good. We have to try to check whether other model will not fit. And what's more, we can check the fingerprints and how to say and check it and think rationally. Check whether okay, we can here have linearity, but it's on the very small area. So maybe, despite that we have this linearity, it's not actually correct. Similarly, here we have linearity, but it's only on the small area. So and so it's probably not right. And but still, sometimes it is how to say difficult to see what exactly model we have to fit, because frankly, this as Professor Danuta was speaking on the previous during previous lecture. Well, sometimes it's not exactly clear which one to fit. Okay, so okay, I will try to go. Okay, I don't know what I did. Okay, okay. So now we want to fit some data. This data was provided by Adriana Kis and Elżbieta Masiewicz. And how we do this? So first, we obviously we have to check magnetization for all frequencies, whether it's single or B exponential. Because when we got relaxation rates, well, the instrument provides us with some relaxation rate, and then we have to manually check whether there is some mistake there, whether there is not additional second component with the magnetization, because if it is, we have to treat it in the case by case basis. Then we try to check whether we see the so-called fingerprints for all data. So it means what I mean by all data. When we have some usually, we are not having just one relaxation rate, but we have a relaxation with quite few data sets. In this case, different temperature all has its own relaxation rates. So when we are checking this fingerprint and actually all this calculation, we have to check for all um, to check whether we can fit it in all cases. Then we try to calculate d from slope, and then we fit to full model, including rotation. Then we check results. Okay, this is, well, let's say, I call this procedure, but it's very important to not treat this as a mathematical algorithm. It's not like we are doing everything in order and well, we have to, how to say, well, maybe we have to think at each step. We have to think logically and try to think whether something is not going wrong. We not just check fingerprint. Okay, we have fingerprint, but we have to, for example, check whether the area where this fingerprint exists, where this linearity exists, is enough. And there is not very, very rare we can say, okay, if the linearity is, for example, from this area to this area, is this enough? No, we have to each time, each data set is different. Each time we have to try to, how to say, uh, well, think rationally, think critically whether our doing is everything correct. Okay, but let's start this procedure. First, we check magnetization. It was done we did this yesterday, but let's do this one more time. Okay, and I said we check for all frequencies because frankly we should check as much as frequencies as it is possible. Usually, it sometimes is done like that. So for example, that when we have many sets, then for one set of data, we check every frequencies to check whether there is no some b exponential in the way, so there is no some problem. And then for different sets, we take, for example, 10 or 20 frequencies and then check to check them. So, for example, here, okay, one moment, because I stop exampling, I have to go to the origin. One moment. I will open it. Okay, and now I will try to share it. Mhm. I believe you should hear see right now the screen. I will now enlarge it. So first step, as I said, it always to check magnetization because, for example, if we first do some fitting, we fit everything is everything, and we get proper results, and then before publishing the article, we decide to one more time check this magnetization, and then we see that this we have to be exponential function in magnetization. Our entire analysis, well, it have to be repeated. Uh, okay, so well, to check this magnetization, as I said before, as I said actually yesterday, we have to try to fit exponential function. And as if we do this in origin, we click here analysis, fitting non-linear curve fit, and here we fit. Okay, so here are all of the parameters of the fit, and we can check. This is the first one. Here we can check just this fit, and as we can see, it looks good. But we can check when this is also put in the graph on our graph here, and I will, of course, on the first glance, it looks correct, and then. Let's enlarge this area here to make sure more or less it's going correctly. It's not perfect fit, but it's quite sufficiently good. Okay, so just in normal way, it should be done for each of the frequency independently. But well, I don't think that you want me to check for 40 or 50 frequencies on the stream because it will be how to it should be done, but it will be not very interesting for you. So let me check one more frequency, for example, this one. And to be clear, I got this data, and I know that Adrian did analysis for it, and she got the results for the 3D translation diffusion, but how to say, I didn't do it. So I am doing this as in, how to say, in the life. Okay, one more time, the K1. And go, let's go this. This actually fit doesn't look the best actually when I look for it. Actually, let me put all other data from this because to see, but it doesn't look good. But how to say, the problem is that we can see a lot of some problem. Actually, why I cannot restore the data to the normal size? Okay. If we can see here, we can see that, well, these results have some errors in the way. So, well, it will be not very good. It will be never be perfect fit for them, and therefore, well, it can still look as it is single exponential. Okay, so now let's come back to the our to the further step of our analysis. Okay, and I will now go to this. One moment. One moment. Okay, I will share with you one more time the origin. These data are as previous. They are this is this data which are read in this representation to checking linearity. So now, and to be clear, this is just a part of the data. It's not full data. If we actually change here scale, uh, change scale, we can clearly see that in at least in the case of 243 kelvins, it's not linear on the entire during entire data set, and we don't expect it to be it. As we have said before, this representation have its limit. Secondary, we and second, because for example, it can have additional motion including in this model. So for example, here we can expect that this may be here, this change of the shape may be results of the results from the this change rotational movement. Okay, so we have here. So let's come back to this area of the from 0 to 1000. And we can see that even in this area, this linearity is not exactly correct. I believe this should be here. Oh, yes, I believe it is. If we here, we have some more or less linearity. Of course, in this area, we have some errors are not negligible, so we are not sure how to put it. But if we go here, we have see that this area is more or less linear. However, if we would put mm, goes up like here, well, we can clearly see that if we go over to this 1000 on this representation on this scale, it's not linear. here it's not linear any longer. Therefore, still it is linear at in some ways, because here it is, let's say, linear to around 700, 700, so it is to around, if I calculate it correctly, to around 500,000 hertz, so 500 kilohertz, 500 kilohertz. So this first result is more or less linear on this small range. So now let's go to the another example. For example, this 200, this second one, and let's read, because right now it's changes so slowly that we cannot see how it change. So let's change the scale here to the 500, let's say. And here do -50. Okay, we have such a result, and frankly, on um, this entire region, this data set is more or less linear. It's not perfect linearity, because we can see that something here is maybe experimental error or something else happening, but it's more or less linear. So now let's change area because it's going up to this limit. So let's enlarge little our downscale, our x-axis to, let's say, 1500. Okay, and now we can see that here it's clearly stopping be linear around this region. Okay. Okay. So now let's do one more time, one last. Let's say this 268. Okay, and it is much smaller. So let's go to 150 and to say, let's say, okay. So actually I have to change more, because here and say here 20. Oh, I put some wrong number, I believe. Yes. Okay. As you can see here, actually here is linearity. It's more or less linear on this in this region. Actually, as before, I want to go even further to check how it's the act further, not just. Oh, there is some chat. Okay. Mm, okay. So now let's go to the check whether this linearity is even further. So let's say to 2000. And here, as we can see, this linearity is still much longer. What that means? Because if we have this first, we have good linearity, so that means that we expect that this result is more or less 3D 3D translation, 3D diffusion. But if we have such results that in the linearity, well, it's it's bigger, going even bigger and bigger, because if we have here, it is around, I believe it is around 2 megahertz of the frequency. So, and the linearity is on the very big in the big area. So this means if we, okay, let me come back to presentation. I will stop presenting here and come back to slides. And okay. and show you one moment. I believe that the slides should be one more time in your window. If we look on how where the limit is supposed to work is where there is well, first, if the limit work, that means that the first we can expect that tau trans it will be going well start decreasing very drastically. It will start with much because how to say when we divide this by tau trans, we have that the angular speed has to be less than 1 over the tau trans. So first, we can expect that tau trans will be decreasing with the temperature, and it will be decreasing substantially. As we can see, this when we going from the 243 kelvins to, let's say, I believe the biggest temperature in the set is to 300, well, the change is substantial. So the change in the tau trans, and if tau trans, then also in the diffusion coefficient, it will be also very substantial. Secondly, we can expect that the second motion we go also start further. It will not be in the smaller, smaller, how to say, in the smaller frequency. Or to be more exact, the rotation, it will be there, but the change of the rotational function, because as you may remember, the beginning, this area and this function is flat, so we don't expect it to change it until around tau rotation. So if it's so that means that if in the linearity is further goes further in the frequency, that also means that this tau rotational it will be also decreasing substantially. Okay, so we have our here we have some examples of the linearity. So now let's go to the fitting of the diffusion. And frankly, when we have this result, this can be calculated using such NH can be calculated, you approximated from such a result like here, and from such formula like here. So let's try to do it. Okay, I have to come back and change one more time in the slide window. And I will try to share it with you, of course, now. I apologize because there will be some going between the windows. A lot, actually. Okay, I believe it is one more time. It is you should be able to see it. And we have actually I need to be able to see the menu because Zoom overlaps it. Okay, so we put here, and we can do it in two ways. We can calculate and just simply do it to fit simple linear function, and we take the slope and put to the some other program, and then calculate from that the diffusion coefficient, because well, this is in this representation it is linear. The second way to do it is, for example, to put these results into the origin. I actually did prepared such function beforehand because I usually prefer when I fit something and take the slope to get already results during the fitting because if I do this during and then get already the diffusion coefficient here, then if there's something which I don't like, I can always check something because it is very, very important that okay, we are checking we are checking the diffusion coefficient, so we check the linearity. It will be some changes depending whether I will start, for example, here, or for example, I will start here. It will change. So it shouldn't change much because we expect it to be linear. So this slope it should be more or less the same, but well, there is always some errors during the fitting. There is always some errors during fitting, and this error can show during where we start our data selection. Okay, here is this function which I will show the. As you can see, I put here this equation which was shown on one of the previous slides, and put, of course, all of the constants into the program. And now Professor Danuta showed already how to create such functions, so I will be not repeating her. I put here a limit how I want where I want to fit, and of course, as we can see, it is not linear to 3000. I believe it should be linear around 750, and we can change from what value we start fitting. And frankly, in this case, I would start fitting from 250. And we can order the program to do the fitting. And we get results 1.79 multiplied by 10 up to minus 13. This is very, very small diffusion, but we have to remember that, well, this is small temperature. In this, and the diffusion grows together with temperature. Therefore, if we and this change can be very, very substantial. So while it is small, it is possible. So, okay, I can got such results here, and as we can see, also we got also here the error. So let's now try to fit another one. Here we can easily fit on this entire area. So let's one more time, and I have to choose data selection. Goes from by x from 100. Let's say it here to 1000. Okay, and of course I forgot to check the function, and let's set a fit. Okay, so what we have here, firstly, as we can see, it's not exactly perfect fit as I expected. It's clearly still not not fitting perfectly, but well, it's more or less linear. And then we have these results of the diffusion. As we expect, it goes up and it goes actually by substantial amount, but it's around, let's say, 2.5 bigger than from the 233. And we should do this for all data sets, and each time check whether the change in diffusion is what we expect. So whether it grows. Because if it somehow start in decreasing, it means that we have some problem. Maybe the problem is from the fit, but in this case of the slopes, it's well, I wouldn't. The fitting is so easy that unless we are making the error in data selections, we shouldn't have got any uh, any problem with the fitting. And let's fit the last temperature. So I'm in 300. I have to check and change window. One moment. And actually, I will try to share the instead of the window, the screen, but from how to say experience, I know that it doesn't always work how we expect. But this because then I will have a little small number of changes. Okay, we have such a results, and as you can see, for 300, this is very the changes are very small. So let's try to fit it. And first, I would like to we have to enlarge it because, well, frankly, right now we don't see anything. So let's say from 5 to, I believe it will be 8 will be more than enough. Okay. And as we can see, this is not from 1000 to the uh, 3000. And we can see that nearly here, this result is more or less linear. I didn't previously show you, 300, but as we can see, well, it sees very long linear. But to not make some mistakes, I will try to fit only to 1500. So analysis, fitting, and I go to my prepare plot. And here we have our results, more or less linear, and we have got our D, which is actually much smaller than than I expected. Okay, we have our actually it's much smaller than I expected. Okay, okay, but hmm. Okay, we have our results. Let's go back uh, to the presentation because next part is actually these are results from Adriana actually, and now next part is try to fit it. To fit not just this slope, this approximation, but to try to fit entire range of the model. And as the Professor Pedro, Professor Krug were talking, we can use many tools. We can use FITEA. We can actually try to fit it into origin. Personally, I prefer to fit it in the script which I prepared in MATLAB, but it is, how to say, my personal preference. The tool doesn't exactly matter here as long as this tool is correct. So I will now go to this tool and I will run it. And we have here this application which I prepare sometimes as I go to do the fitting. Here we have all the parameters which we have to fit to our model. I will come this correlation time and dipolar constants are going to the rotation. So this means actually I believe here is this tau rotation, and of course before every spectral density we have also correlation. I'm sorry, tu mamy also dipolar constants. These two parameters goes to this rotational function. These two parameters and this actually are describing the translation function. So first we have distance or closest approach. Secondly, we have self-diffusion coefficients in this case, and then we have number of hydrogen atom per unit. And in this case of and to be clear, when I hear each of them have three values. First one is initial values, so where our fit will start looking for correct answers. And here I can put a lower and upper bound. And of course, I will import actually data. I believe this is the first one. And well, here we have number of hydrogen per atom. And from that formula, which I was showing you previously, I know that it should be around 6.8 minus, not minus, 20, up to 10, up to power 28. And I am putting it to be constants. And to be clear, during the fit, we have to fix either distance of closest approach or number of hydrogen atom per unit. We cannot put them all three because they are dependent on each other. If we look on the spectral density function, they are here, and therefore, if one number of hydrogen, these they are dependent on each other. The program will not do correct fit if both of them are free. Technically, there is a chance that it would work because this distance is also put in the tau trans, but in practice, it is rarely works. Usually, it makes the program programs starts going stupid, or to be more exact, by fitting this. It's not fitting this, but trying to use this for compensate errors caused from the different from this for fitting diffusion coefficients. So either this or this have to be set constants. In this case, we calculated this number of hydrogen unit per atom, so we can put it here. Very often, instead of that, and then that means that I can this set free. And I let's say that the lower bound will be this 2.78 minus 10. This distance of closest approach is actually significant because it is distance of closest approach for two particles of water. This is the closest as they can get. And frankly, sometimes when we are not sure what put here, then we simply will fix this result to this 2.7 multiplied by 10 up to minus 10. So in other words, 2.7 angstrom. Okay, so and now here I can put it free. I'm sorry. Let's say 1 nanometer. It's very, very big, and frankly, frankly, now we go next step, because we more or less expect what will be self diffusion coefficient, because we calculated it. We calculated it using the slope, so we can try to put it here and fix the result. I believe it was 1.7 up to minus 13, and let's fix it. Okay, so now we can order the program to do the fitting. And frankly, I have to go little here, because here will be put results. So now we will little wait. Then I set a 400 iteration, but the programs found some good fit is much earlier. But when we see on this fit, there is some problems. Firstly, I forgot to put here 2.7, so it's actually these two are closer than atoms of the water. It's rather not expected. Secondly, we can see that this correlation time is, well, much too big. If this correlation here like is such big, it's actually doesn't have to be there. And in the same time, we can put actually, when I think here, I could easily put much bigger up bound for the independent term, because frankly, the program tried to use this by putting such actually, no. He say that there is no component from correlation, and we can see clearly here that because that fit was not perfect, and such fitting slowly trying to get the fits, doing the same fit many time is normal. We don't know the correct values up front. We can try to guess. We can try to more or less uh, uh, how to say, limit these bonds much further. For example, I can say here that it should be like that, but for example, let's put here 0. So if the program decides that there is no correlation time, then it should lower here up to 0. Okay, so I have these results. So one more time. And we have to wait a little, depending. It takes sometimes depending on the problem. Okay. Okay, I forgot to clear the form, figure beforehand. As you can see, well, it's not perfect program, but we get some fit, and the fit was little better than before. Okay, so we got some fit, and the fit look not bad actually. If we can see, well, it will be never perfect, because frankly here we have such well problematic part, because they are, well, they are much different between each other. But if we have did this, then the next part we can try to we get some fit which, how to say, makes sense. So I putting this as the starting value. So the fit will go from here, and I will start actually this. And of course, always we have to make sure that this all the results, how to say, make sense. So we have changed that. Okay, such correlation time is possible. Such polar constant is more or less possible. To be honest, I usually start when I make fitting. I put the area of the fit the bands as wide as possible, because from mathematical points of view, even if the correct answer is in the between the bands, then the mathematical algorithm which do the fitting will want to got to, how to say. Okay, one moment. I will try to do it into. I will use paint to show something, because maybe it will be easier to show. Okay, as we, for example, let's think that here is our starting point, and here are our correct results. We would expect that program goes like here, right? Goes straight to the correct answer. But the problem is that when, I'm sorry, I will check with something, someone wants to speak. I can share it, and or I can probably share another app which we are currently, which was worked by our programmers in our university. I will consult with the Professor Krug about this. Okay, but come back. Let's come back here. The how to say? How to say? Okay, what I want to say. Okay, so we expect that these results go here, but the problem is that at the beginning program, and we said, let's say, the bounds for our system. But the problem is that program doesn't know that here we have correct solution. He has to somehow got here. So I sometimes think about this, how these programs do it. Uh, let's imagine ourselves that we want to check whether the lowest altitude in the region, and this region is mountains. So how we can go to the lowest altitude? We go here later, we go here later, we go here later, we go here later. Oh, actually, I'm sorry, go here later. And then we check where was the lower than our initial point. Okay, here was the lowest point. So we go further. We go from here, we check one area, add second area, third area. The program check every around where it should go to do the fitting. Of course, we would expect that it would go to this area, but sometimes when there may be, for example, here some mountains, I know that my drawing is very, very, very bad. Actually, not that shape. Okay, I forgot. Oh, here, this is here. There is some mountain which he have to go around, because it's not the fitting, the algorithm is not exactly perfect. And if we set our bounds too small, it can, for example, the path to take it maybe goes around these bounds. It's not exactly clear science. Frankly, the fitting, well, as I said yesterday, sometimes in the mathematics or physics, well, there is no craft, there is something more or less art. So there is no clear solution how to do it. But of course, if we set the results as wide as I usually put, we will get sometimes not correct answers. But okay, so now let's try to check different, do another calculation. I'm sorry, another fit, and let's put the fit. Let's say I don't expect it will be very different, so I will start lower of the 1 multiplied by 10 up to 13, and here let's say 1 up to minus 12. So let's check how it looks. I will change here, and I can put in order in him to calculate. Okay, and frankly, we got little different results. These diffusion coefficients we got is little smaller than before, I believe, because before it was 1.79, and distance of closest approach goes little up. So it changes little. But frankly, to be honest, when we go to the parameter which I check which the fit is the best. So in my case of my program is residual. The change wasn't substantial. Frankly, it may be more. It can be either in these previous results or current results because the value and this value didn't change much, and as we can see, well, it look nearly the same. So this is the value which we got. Okay, so now let's go. Of course, we can also try to. So now let's go to another results. So that means for 10, and let's say this. I check here also on the biggest temperature in our data set. So I put this as starting values, these results which I got for the previous one, and actually I would put this as a closest approach on the beginning as constants. So I will fix it. Because we expect the distance of closest approach doesn't change with the temperature. We expect more or less it will be the same. Of course, it can change and it can be little changed, but we first want to check whether it is possible to get correct results, to get the correct function if we keep the distance of closest approach constant. Okay. So independent. Well, I remember that the previous data set it is much smaller result, so it will be not here up to my 1000. And frankly, I would put here 0 independent term. And now let's fit. Okay. Oh, and fit was much worse. Oh, actually, the problem was that I put here this upper bound, and frankly, it will be much bigger. So let's put it. Well, let's put here a value of water in the or in this temperature. So let's check whether the program what will program do now. I can here look here how this residual change. That is actually one of the reason why I'm using this program instead of FITEA, because I can see how the calculations goes. And let's wait a little. And frankly, as you can see, this is another problem with the fitting, because you can see that the calculations are done, but the residual, this parameter which show how good the fit is. But to remember, not it, you have to always remember that it should be interpreted only in this data set and so on, not compared it without that in different data set. Is actually doesn't change it, because going here is actually going circle around correct answer. Or I believe it's going around correct answer. I don't know that. It cannot go to get correct to the correct results. Okay. But for that reason, I put in this maximum iteration of 400. So if I see that it doesn't change for so long, I can review. Oh, actually, it found when near. Okay, and oh, of course, I did a mistake because I forgot to clear the data. I'm sorry. Then now it will be much faster. Oh, yes, now it's work. And we can see that this is going much better than previously. Frankly, what we can see here is actually that the self-diffusion coefficient 200.78 minus 11. I believe that the results which we got from the slope was different, but I would have to check it. And frankly, well, this is one of the things which we have to always check. And secondly, this across doesn't change. What is interesting here is that we can see that mm, uh, technically it fitted the correlation time, but it's more or less doesn't show here because here we have our diffusion. The component of the correlation doesn't show up. It's around here. This one here is this. So if we would enlarge it, so we got to see how big it is. But well, it is not. How to say? It's probably not relevant for this data. So now, if it is not relevant, so now its next step is to say it doesn't exist. It's actually let's check whether if it is so small, whether we can fit without it. So let's do the fitting. And frankly, as you can see, the fit is not much, is nearly identical as previous. Does it mean that this correlation doesn't exist? I don't know, because frankly, it may be also mean that this correlation time is so small that this change from this, as you remember, this rotational the spectral density function was like that and like that. And maybe we are still on this plateau version on the lower frequency. If we actually the fit which was given, the correlation time is actually around, it would be go around here before it would change. We don't know that, but as we can see, we can get very good fit if we forget about existence of rotation altogether. Just it is, let's say, eaten up by frequency independent term. Of course, we can do it second way. We can say, okay, I don't want to be frequency independent term because I believe it is just rotational. So then we put here and we put here. Let's start here from something more um, not such small and insignificant for our data set. And here, let's say. Uh, okay, so let's order set okay and calculate. Of course, actually well, it actually the program didn't fit it correctly. It sometimes happens because well, it's not something is not correct here, but it should fit actually. Actually, let's put here is like that. Yep, and let's put here like let's say that. Okay, it will be better fit than previously, but I don't know how it will be looking. As we can see here in the parameter still change, so I cannot, we have to wait. Oh, frankly, I don't, I will soon be out of time, so I will try to speed up. Just this last fit, and I will go back to the to the slides. If there is some question, then well, I have time a little for now. So if you want to ask something, then ask in the chat or in the voice.
No questions? It's still calculating, yeah, isn't it?
Yes, yes, it is calculating. Okay, so it stopped calculated. Okay, so we got results, and still correlation time it go here up to here and doesn't make any. So it's actually it could be as good as nearly constant in this case. Okay, so now let me come back to my presentation because, well, more or less it will be running out of the time. And here are results, not mine, but which was gotten by Adrian. Why I am showing this in now? Because, well, now when we do the fitting, when we put our parameters which we got into our into table, now is the next part. We have to check whether they how to say make more or less whether they make sense. We have to check whether the diffusion whether diffusion coefficient is increasing with temperature. We have to check whether other parameters also act as we expect them, including with with temperature. So whether tau rotational is decreasing as temperature increase. We can also try to compare these results to other experiment results, or maybe to the molecular dynamics to the theoretical calculation from MD. And of course, we can always try to compare these results to other substance. There is no some to other substance because if, for example, we have some big particle and we get diffusion coefficients faster than water, then we probably should think whether everything which we got is correct. Because frankly, it maybe means that we got some wrong results. Maybe wrong results can be results of many things. Because, well, even if our results doesn't make sense, doesn't mean at the beginning that the model is incorrect. As I said before, maybe using this part, maybe we have find here some region, another minimum, and the program have problem with going out from this minimum. So this is still mathematical problem. Sometimes there is some combination of the values which doesn't make physical sense, but it makes sense from mathematical point of view. Our programs doesn't think. They are not intelligent, and they are just checking this one parameter which they got. If in case of better programs, a few parameters, but that's beyond the point. So therefore, it always can happen some situation that there is some mistake in the fitting. But of course, it can also mean that if, for example, D is increasing, if there is some problem that D, for example, stayed the same during entire data sets, or God forbid, it starts decreasing with the temperature, then well, we have to start to check whether we could did proper fitting, or maybe it's not correct model. Sometimes it's just that model is not correct. Okay, and I wanted to show example from example of fitting 2D, but frankly, we more or less we are run out of time. So if you have because the beyond different model, the procedure is very similar. We first check we first check magnetization, then check fingerprints. In this case, on the x-axis logarithm scale. And then we do fitting to entire the data set. Okay, thank you for your attention. If you have any question, then ask.
Thank you. I fear that now you are of the opinion that it is extremely difficult to analyze NMR relaxation data, and it's not because of Adam lecture. This is not what I wanted to say. That this is but that really after my lecture and Adam lecture, we figure out that the crucial thing is to find the proper model, and it is really not clear what the model stems from and how to choose the proper model. But do not worry, we'll continue. We'll have lectures also tomorrow. And as you have seen, there's this wide, not really dense schedule for tomorrow. There's a lot of so-called free time when we can deal with things. So we'll go through different examples, and this will become more easy to understand. Today it was just a huge load of new information, but step by step. Do you have questions? And sorry, answering to this question, we may not share this MATLAB app at this moment. I can explain why later, but we'll share something similar. I do not see questions, so I can wish you a nice afternoon and evening, and see you tomorrow.